And it's not inconceivable that we're doing an electric plane, but I do think that we're not quite there in terms of the energy density of batteries for an electric plane. I think the kind of minimum that you'd want is about 400 watt-hours per kilogram. At 500, it starts to become quite compelling, but I don't know. I think we're maybe 4 or 5 years away from having 500 watt-hours per kilogram.
Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. Elon Musk has mentioned several times that he'd like to make an electric, supersonic, vertical takeoff and landing jet. Today, I'm going to take you through what I think that would look like, and more importantly, why it would look that way. This video is broken down into 6 parts. What an electric, supersonic, vertical takeoff and landing jet is, and what those words mean, what the design principles would be, applying those design principles, the design itself, some rough calculations, and my conclusion, which, spoiler alert, this thing would be awesome. Vertical takeoff and landing, also known as VTOL, is the ability to take off and land vertically, like a helicopter. The advantage of this is that airports could be considerably smaller, or even better, the entire concept of an airport would be rethought, but we'll come back to this. Supersonic simply means that it will go faster than the speed of sound, which varies depending on temperature and humidity. But let's assume it's 660 miles per hour, or 1,060 kilometers an hour at 35,000 feet. For reference, the average jet speed is 550 miles per hour, or 890 kilometers an hour. Generally, supersonic aircraft are designed for at least Mach 1.6, which is 880 miles per hour, or 1,700 kilometers an hour. This is because drag decreases after you pass through the sound barrier, so we can assume it will be at least Mach 1.6. It's also important to call out what a jet is. Jets don't just refer to the jet engines on modern aircraft that burn fossil fuels to spin a turbine, but any propulsion that uses a high-speed jet of gas or liquid. With an electric jet, it would be a battery-powered motor that spins a turbine instead of exploding fossil fuels that power conventional jet aircraft. For the sake of brevity, for the rest of this video, I'll refer to the jet we're talking about here as the E-SuperVTOL. I also like the sound of it. So where do we start with our design? We'll need to think like Elon Musk for this. First principles thinking underlies everything Elon does. He asks basic questions and tries to get at the core reason why something works or doesn't work. This way of thinking shows itself in several ways. 1. Clean sheet designs. When you use a new technology to replace an existing technology, you need to throw out old thinking and start with a clean sheet. This allows you to make the design simpler, which reduces parts and manufacturing cost. The best part is no part. This is most obvious with the Cybertruck and Starship, which are brutally simple yet effective designs. 2. Technology readiness. Elon pays attention to limiting factors. He won't build something unless the basic technology is at a point where a minimum viable product can be created. He then pushes the envelope of technology forward to create something magnificent. We can clearly see this in how he's led the development of Tesla vehicles, which are the iPhones of the car world. 3. Cheap materials. Elon always uses cheap materials in a clever way. As he puts it, it's just a matter of reorganizing atoms. So, you may as well use the cheapest atoms. An example of this is how Tesla uses cheap magnets in a Hallbach array. A Hallbach array simply means chopping up cheap magnets and gluing them back together in a specific order to make cheap magnets perform as if they are more expensive ones. 4. Redundancy. When it comes to aerospace, Elon uses redundancy to increase safety and reliability. The clearest example of this is the Falcon 9 rocket. 9 small engines is better than 1 large engine. Let's now go into depth on each one of these design principles. Clean sheet design. Conventional aircraft have several aerodynamic inefficiencies and unnecessary complexities that add weight. One of the largest being all the control surfaces that are needed. These add an enormous amount of complexity and weight. This could all be replaced with engines that can turn, also called gimbaling. Gimbaling engines also means no tail would be needed, which also reduces drag quite a bit. Vertical takeoff and landing means the wings would mainly be hard points for the engines to mount on, rather than primary lift devices. This means the wings could be made smaller, meaning less drag. Airplane wings on supersonic jets are always larger than they need to be because they need to generate lift at low speed for takeoff and landing. With vertical takeoff and landing, the engines would simply point directly downwards to take off and land. This also means wheeled landing gear wouldn't be required, but rather landing feet. Landing gear are extremely robust and heavy to absorb the energy of landing. When a conventional jet lands, it's basically a controlled crash. The tires, which are high performance, large, and expensive, also need retreaded or replaced every 150 to 200 landings, which isn't cheap. Unlike conventional supersonic jets, the engines in our design could be mounted away from the body, reducing vibration and noise in the cabin. Supersonic jet engines are heavy, and there are usually only 2 of them. Because of this, they are usually part of the body or close to the fuselage because the wingtips can't handle that much weight. Because we're using multiple engines, they could be smaller and lighter and mounted further from the body or even on the wingtips. The nose of a conventional jet is rather snub-nosed. The reason for this is it makes the most of the internal volume and because they aren't traveling at particularly high speeds. The nose on our design could be very long and pointed, which would make it very aerodynamic. The odd-shaped space in the front could be filled with batteries, which can fill about any shape. Overall, in terms of design, Elon likes designs that are a fusion of perfect form matching perfect function. Think the Cybertruck and Starship. The designs are simple, brutalistic, and functional. Technology readiness. Battery-powered jets aren't feasible until battery energy density increases. Think of energy density as the fuel tank. Currently, Tesla's batteries are 250 watt-hours a kg. Elon has stated that 400 to 500 watt-hours a kg would be required for an electric jet. This is definitely a minimum. With that density, the jet would probably have half the range of a conventional jet. We'll get more into this later. We should be expecting 500 watt-hour kg batteries by the mid-2020s. I think this is when Tesla will devote a small design and engineering team to start developing the E-SuperVTOL. It takes about 5 to 10 years to get approval and start production of a jet. This puts us in the early 2030s when this jet would be revealed. This is when battery densities should be hitting about 1,000 watt-hours a kg. So by the time the jet launches, it should have a solid range. Tesla also wouldn't devote heavy resources to this project until they've gone a long way to electrifying the global auto fleet, which should occur around 2030. This would give them plenty of time to finalize the design, gain regulatory approval, and set up manufacturing for a mid-2030s launch. Let's start getting into jet motor design. The electric jet motor would need to hit between 10 to 20,000 RPM, but this depends on if it's geared and on the turbine design. The turbine is the fan that sits within the jet to push air. The engines on a Boeing 787, for instance, hit 11 to 13,000 RPM, but we're going supersonic rather than Mach 0.85. No gears is preferable, because that means more simplicity, less maintenance, lower weight, and longer life. Tesla's Model 3 motor hits 18,000 RPM, but electric motors tend to be more efficient at lower RPM. So we may need to fundamentally redesign the electric motor for high-speed power rather than low-speed torque and efficiency. Current electric motors are too heavy for an efficient electric jet. They are low power density compared to gas turbine engines. Efficient commercial jet engines produce about 10 kilowatts of power per kg of weight. A Model 3 motor produces 2 kilowatts per kg of weight. This would mean an electric jet motor would be 5 times heavier than an efficient commercial jet engine. The reason why electric motors have low power densities is that large electric motors suffer from heat rejection issues when they get very large, meaning they are very hard to cool down and so need a large cooling system, which creates weight. Luckily, NASA is working on this cooling problem with Ohio State University and have achieved 4.7 kilowatts per kg using a novel cooling system. This is excellent, especially considering they were using low-quality magnets. Their goal is 13 kilowatts per kg with a better design and higher quality magnets. So, my guess is that by 2030, we can expect a high energy density electric motor competitive with gas turbine jet engines. NASA's work is just the start of this, and we have a decade to refine the technology. Cheaper materials. Tesla could again employ the Halbach array magnet setup used in the Model 3 to improve upon the electric jet motor I just mentioned. Supersonic jets are made of expensive, lightweight composite materials that are durable at high temperatures because the aircraft gets super hot from air friction at supersonic speeds. The composites that are used can also be formed into nuanced shapes, which is necessary because conventional supersonic jets need to perform well at both low and high speed, which takes a complex and nuanced wing shape. This looks like another job for Elon's favorite material, stainless steel. It has a great strength-to-weight ratio at room temperature, but at high temperature it has a superior strength-to-weight ratio. Stainless steel is cheap compared to the complex composites in conventional jets. It will also be easier to tool for and manufacture. One added benefit of a solid stainless steel tube is that it could operate at a higher pressure. It could operate at sea level pressure, for instance, and it would have a higher resistance to moisture. Take those two things into account, and this would mean no more ear popping, swollen feet, and dehydration common with flying. One of Elon's specialties is creating pressure vessels, and is becoming an expert in creating them out of stainless steel. And that's essentially what we'd be talking about here. The fuselage of the jet would become a stainless steel pressure vessel. Redundancy. A VTOL with decent maneuverability and stability would need at least 4 jet motors to provide stability, like a quadricopter. However, electric motors would be easier to manufacture than jet engines due to fewer moving parts and no need to control an ongoing superhot explosion. So, it would improve safety and stability to use at least 6 electric jet motors. That covers off our design principles. It's time to take a look at what I actually created based on those design principles. Let's go through some of the key points of the design, both in terms of what I think is good about it and things that could potentially be changed or improved. So, what's great about the design? Aerodynamic shape, which I'll do more analysis on when we get to calculations. Gimbaling jets instead of control surfaces greatly simplify the overall control system. Small delta-shaped wings and winglets to reduce drag and also reduce sonic boom. The sonic boom is a key limiting factor for conventional supersonic jets. These booms are very loud, and it makes flying over land prohibitive. Since most flights are over land, past supersonic jets had limited utility. However, NASA and private companies have nearly solved this problem and are currently developing prototypes. I've designed these small wings to be similar to the Skylon jet design, which, if it ever makes it to production, will be the fastest jet ever produced because it would enter low Earth orbit. As you can see, it's tubular and has small delta wings. I did consider a bidirectional flying wing shape, but this would prove to be too complex to incorporate into a VTOL design, and would be somewhat redundant. Bidirectional flying wings change their orientation by 90 degrees between supersonic and subsonic flight. It's a fascinating solution, but in my view is optimized for runway takeoff and landing rather than VTOL. The landing gear are feet instead of wheels, which reduces weight. The tubular design is easy to manufacture and has many other side benefits, like an improved flight experience discussed earlier. Multiple engines of the same size create redundancy, safety, and manufacturability. The batteries and weight would mainly be at the nose and possibly some at the rear, making use of that odd-shaped space. There would be no cockpit due to autonomy. This gets rid of unused space and weight. There would be no windows with screens instead, which greatly reduces manufacturing complexity, increases rigidity, and reduces weight. Wingtip motors provide more stability than conventional VTOL, which is often vectored and along the center line. Vectored thrust simply means that the thrust is diverted or power is redirected to flow downward from a fixed engine. As you can see here, this is wobbly, complex, and inefficient. Let's get to what could be wrong with my design. It might be that the entire wing mount would gimbal instead of just the engine. This would give more control but require larger control motors for gimbaling. The distance from the engines to the fuselage. If the engines are too far from the body, the wings might not support them. If the engines are too close to the body or part of the body, they would generate more noise and maintenance would be more difficult. The engines are relatively small because there are 6 of them instead of the standard 2. Supersonic engines are typically narrow and long rather than wide and short. This is to super compress and focus the jet of air. If they were longer, the wings might need to be mounted higher to provide clearance for takeoff and landing. Depending on the top speed and the amount of lift required for maximum efficiency, the wings could be made smaller to reduce drag. The fuselage might need to be thinner to reduce sonic boom and decrease drag. I've used very rough estimates for drag and don't know how airflow would move around this jet, which would require high-powered aerodynamic modeling. And finally, the wingtip motors of the large primary wing might need to be changed. Propulsion at the wingtips can cause issues if one of the jets failed. It can torque the jet sideways. The 6-engine design would probably compensate for this, but the alternative is to make the primary wing smaller or move the jets on the primary wing underneath and near to the fuselage. Time for some calculations. Jet fuel has an energy density of 12,000 watt-hours a kg. We'd be targeting a 1,000 watt-hour a kg battery. So, jet fuel has 12 times the energy density. But how much of that fuel actually turns into motion? In the best engines, both internal combustion and gas turbine, about 50% of the energy is turned into motion. Most of the energy is burned up to produce heat. For electric, greater than 75% of the energy is converted into motion, and that's a conservative figure. 12,000 watt-hour a kg jet fuel at 50% efficiency means the effective number is 6,000 watt-hours a kg. 1,000 watt-hour a kg batteries at 75% efficiency means the effective number is 750 watt-hours a kg. So, 6,000 divided by 750. This leaves jet engines with an 8x advantage on power density, but we're far from finished. Our E-SuperVTOL would be a much more efficient shape and could have 40% less drag. If we factor that in, we'd have jets with only a 5x advantage versus the 8x just mentioned. The 40% estimate could be higher or lower, but it looks like a safe middle ground after reducing the wing size, removing the tail, using a more aerodynamic fuselage, and using an engine optimized for the wing shape. One of the largest inefficiencies in conventional jets is that the engine bypass doesn't match the wing sweep. In plain English, the engine is basically a huge fan that operates efficiently at low speeds, whereas the wings are swept back for high speeds. This creates a conflict that forces the engines to run at higher speed and lower efficiency. Cost of fuel and maintenance is the kicker here. Training schools have found that their electric trainers are 1/10 the cost to run in terms of fuel and maintenance costs, meaning they have a 10x advantage over conventional propeller planes. So, total efficiency and power, taking into account fuel savings, would mean that an electric jet is half the cost to run. This is the 5x advantage that jets have, taking into account the 10x savings in fuel costs that electric has. Divide them, and you're left with a 2x advantage in favor of electric. Now, let's say that the E-SuperVTOL needs to use twice as much fuel to go supersonic. Going twice as fast causes air resistance to quadruple, but we can make up for some of this by flying higher. I'll come back to that. This would mean that for the same price as a regular plane ticket, you could get to your destination in 1/3 to half the time. I've seen the point made several times that modern jets lose weight as they fly, which gives them an advantage. However, I think we can more than make up for that because we remove the cockpit weight due to the jet being autonomous. We remove the complex and heavy landing gear. We remove the complex and heavy control systems. Furthermore, electric jets have a few unique abilities that give us more efficiencies. Electric jets have the ability to regenerate energy as they descend for landing, whereas in gas turbine engines, the engines are just creating drag and using fuel all the way down. This regenerates up to 13% of the battery energy on a short flight. Longer flights would be lower, but still significant. Next, we can fly higher and in thinner air, because the engines don't use oxygen. Thinner air means less drag and greater efficiency. Conventional jets are limited to about 42,000 feet or 12,800 meters. At 60,000 feet or 18,000 meters, the air is 10 times thinner. The E-SuperVTOL might be able to go even higher. And finally, our E-SuperVTOL would not need afterburners to go supersonic, which are extremely inefficient and comparable to dumping fuel out the back of the jet and setting it on fire. Note that we haven't taken into account runway maintenance costs for massive airports with huge runways, a jet that would be much cheaper to produce, the cost of pilots, the extra cost of storing food and supplies that longer jet trips require, accommodations for stewards and stewardesses for long flights, and reduced airport security. An autonomous plane couldn't be hijacked. We would also need to take into account that our E-SuperVTOL jet would last much longer if it were made of a tube of solid stainless steel with no windows. Windows create weak points in the structure and could be replaced with screens. Our E-SuperVTOL might have a nearly infinite lifespan with a battery replacement every decade or so, at which point battery performance and efficiency would have increased and the plane would become faster, better, cheaper. A supersonic jet would also be able to do more trips per day, which would mean more revenue per hour of flight. Range would depend on many factors, but it's worth noting that we don't necessarily need to start with a jet that has the range of a conventional jet, which can travel 3,000 to 9,000 miles before refueling, or 6 to 18 hours of flight time. With those factors in mind, here's the conclusion I reached. My base case is one in which the jet wouldn't be developed by Elon Musk, but rather someone that's not an engineering genius or born disruptor. In this case, the mid-2030s, an E-SuperVTOL would have the capability to cover the bulk of U.S. flights, which are short haul. Short haul is up to 750 miles, or 1,200 kilometers, which is up to 3 hours. The E-SuperVTOL would instead take 1.5 hours. These flights would be the same cost or cheaper than conventional airfare and would utilize a 1,000 watt-hour/kg battery. They would use typical materials. That would mean an experience comparable to current flights. Relatively unpleasant if you are in coach. My Elon Musk disruption case turns out like this. All the things that I washed out of my calculation to create the conservative estimate in my base case are factored in. Elon said these jets would become feasible at 500 watt-hours/kg, which would allow the short-haul scenario in the base case. However, with a 1,000 watt-hour/kg battery, medium-haul flights would become feasible. These flights would be up to 2,500 miles, or 4,000 kilometers, and up to 6 hours, or roughly New York to LA, putting the entire continental US within range. New York to LA would take 2.5 hours instead of 5 hours. This would be generation 1. The Elon Musk factor would mean he would start his own airline, which would have its own E-SuperVTOL ports that are smaller and at more convenient locations, a jet with an extremely minimalistic yet comfortable interior, booking would be streamlined through a slick app, security would be low effort, and the in-flight entertainment and connectivity would be top tier. Generation 2 would make trans-Pacific and transatlantic flights available. This would require a 2,000 watt-hour/kg battery, but would incorporate design efficiency improvements from Generation 1 to reach long-haul flights that are 6,000 miles or 12-hour flights. Personally, I'd be looking forward to the 12-hour flight from New Zealand to the US being 6 hours or less. I've assumed in both Elon scenarios that the ticket prices would be the same as other airlines, and that the cheaper operating costs would translate into more legroom and better customer service, rather than cheaper ticket prices. Elon tends to democratize luxury rather than lower prices. Personally, I think Elon will be investing all of his energy past 2030 on developing his Mars colony. This is the main goal of his life, and everything else is in service of that and to fund it. However, I do think he will leave the plans with Tesla and the jet will at least get made. As I mentioned in the beginning, this is a long way off, but we have plenty to look forward to in the meantime. There's a lot going on in transportation innovation. Electric flight is already here, with the Pipistrel Alpha Electro already in use and showing great benefits as a trainer. In New Zealand, it's reduced the cost of flight training from $250 to $90 per hour. We've also seen the development of VTOL solutions like the Volocopter and Lilium Jet, both of which have prototypes. These are expected to begin production in the next couple of years. And, of course, Uber has been working on autonomous VTOLs for local and regional flights. There are also multiple supersonic conventional jets in development. The one I'm following most closely is the Boom Overture, which will test its demonstrator aircraft this year and aims to deliver production aircraft between 2025 and 2027 that will operate at Mach 2.2 and cost the same as a business class ticket. If you'd like me to do a video on any of these, let me know in the comments below. I'm very eager to read your comments and the feedback below. The main goal of this video was to put all the factors I could into one video so people could come to their own conclusions and put forth their own ideas about what this E-SuperVTOL might look like. As always, if you enjoyed this video, be sure to like and subscribe below. I also started a Patreon. You'll find the details of that in the description. That's all for the day. I'm Jordan Gieseke. This is The Limiting Factor, and thanks for tuning in.